Hello and welcome to 9.8 Power Series. Power series is a way of representing functions as a series. The definition of a power series is if x is a variable, then an infinite series is the form the sum then goes from 0 to infinity of a sub n x to the n equals a sub 0 plus a1x plus a2x squared plus a3x cubed plus dot 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 plus a sub n x to the n plus dot 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 means it goes on forever, it's infinite, is called a power series. More generally, an infinite series of the form the sum n goes from 0 to infinity of a sub n times the quantity x minus c to the n would be a sub 0, a1 times x minus c, 8 plus a2 times x minus c squared plus a3 times x minus c cubed plus dot 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 a sub n times x minus c to the n plus dot dot dot. That would be for a power series centered at c, where c is a constant. So the first one we'd see would be like if c was 0 for the first one here. Okay, example 1 says state where the power series is centered. So we have the sum n goes from 1 to infinity of negative 1 to the n times 1 times 3 times dot 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 times 2n minus 1. This generates odds over 2 to the n times n factorial x to the n. Well, if you were to project this out, this would be like negative 1 times 1 over 2 to the 1 power times 1 factorial times x, plus the next term when n is 2, then it'd be positive 1 times 3 over 2 to the 2 times 2 factorial x to the 2 power, plus, and then we'd have negative 1 times 3 times 5 over 2 to the 3rd power times 3 factorial x cubed plus. But the key to this, it should be x minus c to the n power, and since we have x to the n power, that means c must be 0, so it's centered at 0. Okay, feel free to pause it if you'd like. I'm going to scroll this up. Theorem 9.2, convergence of a power series. For a power series centered at C, precisely one of the following is true. Either the series converges only at C, or there exists a real number r which is greater than 0, such that the series converges absolutely for x minus c is less than r, and diverges for the absolute value of x minus c being greater than r. And in that case, r is called the radius of convergence, so it converges for a set of values. So we have first case a one value, then a range of values, then in the third case it converges everywhere. So those are the three possibilities. The number r is called the radius of convergence as a set of the power series. If the series converges only at c, the radius of convergence is 0. If the series converges for all x, the radius is infinity. The set of all values of x for which the power series converges is the interval of convergence of the power series. Let's look at example 2 here. Find the radius of convergence of the power series. The sum n goes from 0 to infinity of negative 1 to the n x to the n over n factorial. So to do this, we're going to do the ratio test. So we're going to look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. That's the limit as n goes to infinity of the absolute value of negative 1 to the n plus 1 x to the n plus 1 over n plus 1 over negative 1 to the n x to the n over n plus 1. So this is going to be the limit as n goes to infinity of the absolute value of negative 1 to the n times negative 1. That's our negative 1 to the n plus 1 times x to the n times x. That would be x to the n plus 1 over n plus 2 times, be the reciprocal of this denominator fraction, n plus 1 over negative 1 to the n, x to the n. So the cool thing here, some things will cancel out. I think I have our red out because the red's going to show up really well. Probably better than green would. Okay, so we have negative 1 divides out, negative 1 to the n I should say, x to the n divides out. So what we're left with is the limit as n goes to infinity of the absolute value of negative 1 over negative 1 times x I should say, times n plus 1 over n plus 2. And really I can take this out. Negative 1, first of all, the absolute value of negative 1 is 1, so that's going to go out. And then we have this x, the absolute value of x, that can come out. And then we have the limit as n goes to infinity of n plus 1 over n plus 2. So we just have the absolute value of x times 1, which is the absolute value of x. Okay. So this converges by the ratio test for the absolute value of x less than 1. Because by the ratio test, if your limit is less than 1, it'll converge. So it'll converge by that. So r equals 1. And x would be the interval from negative 1 to 1. It's the open interval. So again, we take the limits, absolute value of x times the limit. That's absolute value of x times 1. That's absolute value of x. Well, by the ratio test, if the limit, this limit, results in absolute value of x, as long as it's less than 1, it converges. So the absolute value is less than 1. That means our radius must be 1, and that means that it's on the interval from negative 1 to 1. So I'm going to go on to example 3 here. It says find the interval convergence of the power series. Be sure to check for convergence of the endpoints of the interval, it says. So this is a geometric series. Because you have x over 2 to the n power. So in a geometric series, the absolute value of the ratio, if it's less than 1, it converges. So we don't have to use a ratio test here. So the x over 2, the absolute value of that must be less than 1. So that means negative 1 is less than x over 2 less than 1. And that means that negative 2 is less than x less than 2. So the interval of convergence is negative 2 to 2. Now if we went back and plugged in negative 2 here, negative 2 over 2 is negative 1. The absolute value is 1, and that's not going to be less than 1. If I plugged in the 2, 2 over 2 is 1. Absolute value of 1 is 1. That's not less than 1. That's equal to 1. So this is our interval of convergence here. Okay. Feel free to pause that. I'm going to go ahead and scroll that up now. Okay, for example 4. This is find the interval convergence of the power series. Be sure to check for convergence of the endpoints of the interval. So we have the sum n goes from 1 to infinity, negative 1 to the n plus 1 times x minus 5 to the n over n times 5 to the n. So I'm going to do the ratio test. And remember with the ratio test, the absolute value has to be, or sorry, the limit has to be less than 1. See if I can get a little more space out of this. Okay. So we're going to take the limit as n goes to infinity of the absolute value of our n plus first term would be negative 1 to the n plus 2 times x minus 5 to the n over, n plus 1 over n plus 1 times 5 to the n plus 1. That's going to be over negative 1 to the n plus 1 times x minus 5 to the n over n times 5 to the n. See if I can fit this in here. The limit as n goes to infinity of the absolute value of, that's negative 1 to the n plus 1 times negative 1, x minus 5 to the n times x minus 5 over n plus 1 times 5 to the n times 5 times the reciprocal now of this denominator, n times 5 to the n over negative 1 to the n plus 1 times x minus 5 to the n. Sure you see that all in the frame. I know the light's not on that part. And there we go. So, the negative 1 to the n plus 1 is going to go away. X minus 5 to the n is going to go away. 5 to the n is going to go away. And because the absolute value of this negative 1 is going to go away as well. So this will give us the limit as n goes to infinity of negative 1 times x minus 5 over 5 times n over n plus 1. So I can pull this part out. The absolute value of x minus 5 over 5 times the limit as n goes to infinity of n over n plus 1. Well, this limit's just 1. So it's the absolute value of x minus 5 over 5 times 1. So the absolute value of x minus 5 over 5 must be less than 1, because the ratio test says that the limit has to be less than 1 for convergence, the limit of the ratio. So that means the absolute value of x minus 5 is less than 5 by multiplying both sides by 5. So we have negative 5 is less than x minus 5 less than 5. And by adding 5, we have 0 is less than x less than 10. Now we're going to check the endpoints. Okay, let's check if x equals 0. If x is 0, we have the sum as n goes from 1 to infinity of negative 1 to the n plus 1 times 0 minus 5 to the n over 5 over n times 5 to the n. So what do we have? It's going to be the sum as n goes from 1 to infinity of negative 1 to the n plus 1. Now 0 minus 5 is negative 5, so this could be treated as negative 1 to the n times 5 to the n over n times 5 to the n. So these are going to divide out. And then negative 1 to the n plus 1 times negative 1 to the n. That means you're always going to have a negative there. We have the sum as n goes from 1 to infinity of negative 1 over n, essentially. And this will diverge. You could factor out a negative 1, and you end up with 1 over n. It's a harmonic series. So let's check the other one. What if x equals 10? We'd have the sum as n goes from 1 to infinity of negative 1 to the n plus 1 times 10 minus 5 to the n over n times 5 to the n. I'm going to erase this part. This is all in the notes too. You can see those linked. So it's a sum as n goes from 1 to infinity of negative 1 to the n plus 1, 5 to the n over n times 5 to the n. And of course, the n 5 to the n's go away. So in this case, what's different here, n goes from 1 to infinity of negative 1 to the n plus 1 over n. So what's different with this one is, this is alternating. The previous one was always going to be negative. This one is positive, negative, positive, negative. This is the alternating harmonic series, and that will converge. So the interval is from 0 to 10. So the 10 gets to be included. That's it. Okay, so feel free to pause that one. I'm going to go on to the next. Last page of this lesson. Theorem 9.2.1, properties of functions defined by power series. Okay, it says if the function given by f of x equals sum n goes from 0 to infinity of a sub n times the quantity x minus c to the n, we've seen that, equals that, we've seen it, has a radius of a convergence of r which is greater than 0. Then on the interval from c minus r to c plus r, f is differentiable and therefore continuous. Moreover, the derivative and the antiderivative of f are as follows. The derivative would be n a sub n, where n goes from 0 to infinity, times x minus c to the n minus 1. So it's essentially taking the derivative, and that power comes out front. And it goes on in this manner. And I should have had more terms here. Actually, it should say this. It should say a sub 1 is the first term that will show up. And then 2a sub 2 times x minus c plus 3a sub 3 times x minus c squared plus in that manner. Whereas the antiderivative is going to be some constant, remember that for antiderivatives, plus the sum n goes from 0 to infinity a sub n x minus c to the n plus 1 over n plus 1. That's c plus a sub 0 times x minus c plus a sub 1 times x minus c squared over 2 plus a sub 2 x minus c cubed over 3 plus dot dot dot. So let's look at example 5. It says write an equivalent series with the index of summation beginning at n equals 1. So we can change the index for the summation is what this is talking about. This one starts at 0 now. We want to go to 1. So if we start the sum as n goes from 1 to infinity, we just have to adjust what's up here. So now instead, when you put 0, you get 0 plus 1 is 1 for this power for the negative 1. Now if you just put n here, your first term is going to be 1. See, 0 plus 1 is 1. Now if I put 1 up here, I get the 1. Before I took n plus 1 here, so by putting 0 in there, the first term was 1. Now we could just say it's going to be n. But here's where it's different, bigger difference. This is x now to the n minus 1. Because if you put 0 in there, the first term was 0. Put 1 in here, 1 minus 1 is 0. So that's it. And again, feel free to pause. I'm going to go on to example 6. It says find the intervals of convergence of f of x, f prime of x, f double prime of x, and the integral of f of x dx. Include a check for convergence to the endpoints of the interval. So in our first case, this is a ratio, a geometric ratio. So geometric series, so that the absolute value of x over 2 needs to be less than 1. And we saw this earlier. So negative 1 is less than x over 2, less than 1. So negative 2 is less than x, less than 1. No, less than 2, excuse me. So it's going to be from negative 2 to 2. We can't use the endpoints on that one because it's a geometric series. For B, it says f prime of x. So f prime of x is going to be the sum where n goes from 1 to infinity of n times 1/2 times x over 2 to the n minus 1. That'd be like saying the sum as n goes from 1 to infinity of n over 2 times x over 2 to the n minus 1. So we can use a ratio test here. And we do the limit as n goes to infinity of the absolute value of n plus 1 times x to the n minus 1 plus 1 over 2 here and a 2 to the n minus 1. So it's 2 times 2 to the n minus 1 plus 1 over our n over 2 times x to the n minus 1 over 2 to the n minus 1. This is going to be the limit as n goes to infinity of the absolute value of n plus 1 times x to the n over 2 to the n plus 1. In fact, I'm just going to call this 2 times 2 to the n for canceling's sake. Maybe I should call this x to the n minus 1 times x for canceling purposes. Down below here, this is going to flip up. That becomes 2 to the n over n times x to the n minus 1. Okay, so 2 to the n goes away, x to the n minus 1 goes away, and we're left with the limit as n goes to infinity of the absolute value of x over 2 times n plus 1 over n, which is going to be the absolute value of x over 2 times the limit as n goes to infinity of n plus 1 over n, which is the absolute value of x over 2 times 1. So the absolute value of x over 2 must be less than 1. So what we saw earlier, we're going to have negative 2 less than x less than 1. We should check less than 2. I keep saying 1. We should check our endpoints. So if we have x equals negative 2, we'd have the sum as n goes from 1 to infinity of negative 2 over, no, that's n over 2 times negative 2 over 2 to the n minus 1, which is going to be the sum n goes from 1 to infinity of n over 2 times negative 1 to the n minus 1. So this would be alternating positive and negative, but here we have n over 2. That's going to diverge. And then in the second case, for x equals 2, we'd have the sum as n goes from 1 to infinity, n over 2 times 2 over 2 to the n minus 1. That just can be the sum as n goes from 1 to infinity of n over 2. That's going to diverge. So we can stick with the interval from negative 2 to 2 for that one. So feel free to pause it. I have to erase this so I can do parts C and D. So it's time to pause. Pause in 5, 4, 3, 2, 1. Now I'm going to clear the board and go on to part C. Okay, part C. We're doing the second derivative, and our second derivative is going to be the sum as n goes from 2 to infinity of n over 2 times n minus 1 over 2 times x over 2 to the n minus 2. So if we do the ratio test, take the limit as n goes to infinity of the absolute value of n plus 1 over 2 times n minus 1 plus 1 over 2 x to the n minus 2 plus 1 over 2 to the n minus 2 plus 1 over n over 2 times n minus 1 over 2 times x to the n minus 2 over 2 to the n minus 2. Limit as n goes to infinity of the absolute value of n plus 1 over 2 times n over 2 times x to the n minus 2 over 2 to the n minus 2 times x over 2 times all this stuff 2 over n times 2 over n minus 1 times 2 to the n minus 2 over x to the n minus 2. Things will cancel out now. Let's see here. This 2 and that 2. This 2 and that 2. That and this should have been a 2 here. That, and that. So we're left with the limit as n goes to infinity of the absolute value of, we have the x over 2 times, we have n plus 1 times n over n times n minus 1. And those n's can go away. So it's absolute value of x over 2 times the limit as n goes to infinity of n plus 1 over n minus 1. So the absolute value of x over 2, and that has to be less than 1. So again, negative 2 to 2. By the previous arguments, the endpoints would still produce either the alternating negative 1 or not. So this is going to, they would diverge. So this is your radius of convergence. Let's do the last part, part D, where we're talking about the integral. So go ahead and pause that if you need to pause that. 5, 4, 3, 2, 1. And for the last one, part D, we're looking at the integral of f of x dx, which is the sum as n goes from 0 to infinity of 2 over n plus 1 times x over 2 to the n plus 1. So if we do the limit as n goes to infinity of 2 over n plus 2 times x to the n plus 2 over 2 to the n plus 2 over 2 over n plus 1 times x to the n plus 1 over 2 to the n plus 1. That's going to be the limit as n goes to infinity of the absolute value of 2 over n plus 2 times x to the n plus 1 times x over 2 to the n plus 1 times 2 times n plus 1 over 2 times 2 to the n plus 1 over x to the n plus 1. Now things are going to go away here nicely. That goes, this goes, and let's see, a 2 is going to go like that. So we're left with the limit as n goes to infinity of x over 2 times n plus 1 over n plus 2. So we have the limit, I'll do absolute value of x over 2 as n goes to infinity of n plus 1 over n plus 2, and that's just going to be the absolute value of x over 2 times 1. So absolute value of x over 2 needs to be less than 1. Okay. So we have negative 2 to 2 again for our interval. Now if we check the endpoints, we'll check x equals 2. That'd give us the sum as n goes from 0 to infinity, 2 over n plus 1 times 2 over 2 to the n plus 1. That's the sum as n goes from 0 to infinity of just 2 over n plus 1, and that's going to diverge by harmonic series. The last case, x equals negative 2, to the sum n goes from 0 to infinity of 2 over n plus 1 times negative 2 over 2 to the n plus 1. That's going to be the sum as n goes from 0 to infinity of 2 over n plus 1 times negative 1 to the n. This will converge because it's alternating harmonic series. So our interval is negative 2 to 2. Okay, that's it then. Send me your questions and we'll meet online. Thank you. Have a good day.